All right, so last presentation of the day, so bear with me. So I'm going to talk about combustion processes and trying to also put combustion in a little bit the context of wildland fires, also relate to combustion to pyrolysis as described by Dr. Stolyarov in the previous presentation. So this is the outline of my talk, so bear with me, there are 6 sections. So combustion is a pretty wide topic. You can have combustion under different conditions in different configurations, and I'm going to basically focus primarily on one particular configuration of interest that is relevant to fire safety engineering application and to wildland fire. So we are going to consider that our fuel is in solid form. We're going to consider primarily flaming combustion. We're going to consider primarily non-premix combustion. And we're going to consider that the flames are buoyancy driven and that the flames are turbulent. And I'm going to go back to each one of these adjectives in the next few slides. I'm going to spend particular attention on the coupling between pyrolysis and combustion. Pyrolysis provides the fuel to the combustion process for thermal degradation, as explained in the previous talk. And combustion provides the heat in the fire problem. And so both are important, both are coupled together, and that's part of making the problem of describing fire spread difficult. I will, like Dr. Stolyarov, talk a little bit about what's happening in the solid phase, but not so much. That was more his part, but I will emphasize that you have, in addition to pyrolysis, which is production of the fuel, you have also drying phenomena occurring inside the solid phase, and that's important. And you have also char oxidation, which is a dominant reaction for smoldering. So this combustion regime without a flame, and I will talk a little bit about. To talk about combustion, you can go into great details of chemistry, but in fact, we will not do that. And I'm myself more heat transfer, fluid mechanics person, as far as combustion is concerned, rather than a chemical person. And I think this is also for good reason. We will use a global combustion equation model to describe basically the transformation of fuel and oxygen to combustion products, primarily carbon dioxide and water vapor. And when you get at that level, you have already 90% of the story of chemical change due to combustion. It is about right, and that's good enough for us in fire application. This is good enough also to differentiate between over-ventilated and under-ventilated fire conditions, which is an important aspect of fire systems. The combustion chemistry, I will mention it in passing to basically lead to the conclusion that we don't really need it. Of course, there are exceptions to this statement, but when a flame is established, typically the flame is quote-unquote infinitely fast. Infinitely means much faster than other mechanisms at play in combustion processes, in particular the transport of fuel and oxygen to the flame zone. And so you're going to be rate limited by the slowest process, so you can forget about combustion, about chemistry. Chemistry, in our eyes, is going to be infinitely fast. There are exceptions to this. Tomorrow, Sarah McAllister will talk about ignition. Okay, so in ignition, you are starting from no combustion at all, and you're going to the development of a flame. And so in that transition, chemistry plays an important role. Extinction is another similar problem where chemistry plays a role. So, and if you start looking at the composition of the fire smoke, then you need to pay attention to chemistry, because they are actually chemical processes that are much longer than we typically assume in combustion processes, and that are responsible for details of the composition of the fire smoke. Okay, so at the level of my presentation today, chemistry, and I will make that point, is going to be considered infinitely fast, which is a way for us to avoid having to talk about chemistry when we talk about what controls the structure and the rate of combustion of flames in fires. But again, there are problems where you need to pay more attention to chemistry than what I'm going to do here. So first, we are in particular interested in fire spread. Again, this is a topic that will be developed tomorrow by Sarah McAllister and Guillermo Ren. So you can view fire spread in structure fires or in wildland fires as a repeated cycle of heating, thermal degradation, and produce fuel for the gas phase combustion processes, and finally combustion in the gas phase. So you have basically 3 steps. Again, Sarah tomorrow will talk more about heating. Stas just talked about the production of flammable vapors due to pyrolysis, and I will say a few words as part of my presentation here as well. But basically, I'm going to talk about one of the 3 steps in that sequence that is responsible for fire spread. The terminology is important. It's not perfect in the fire safety engineering literature. So pyrolysis for us refers to the thermal degradation of solid fuels and the production of flammable vapor. So it's a gas phase change. It's a phase change from solid to gas transformation of hydrocarbons. Combustion in my presentation is going to correspond to the gas phase oxidation of this fuel that is going to burn with ambient oxygen. Combustion tomorrow morning by Guillermo Ren will also include smoldering, which takes place inside the solid fuel. And ignition is not very well defined. I think Sarah will talk about this. It's either referring to the start of the pyrolysis or the start of combustion, depending on context. So for us, I'm just going to go for the next few slides that try to put the combustion problem in fire into a wider framework. But for us, combustion is an oxidation reaction between hydrocarbons that are produced by solid fuels. So the picture on the left is the one that is relevant to us for wildland fires. We're going to assume that the oxygen comes from air, and so that's the case for wildland fires. And so again, these hydrocarbons are initially present in solid form, and so you need a phase change process, this thermal degradation process, to take these hydrocarbons from solid form into vapor form, so where they can burn in the flame. I have too many buttons in front of me. I'm getting confused. So combustion can take place with a flame, which is going to be my assumption in the remaining of the talk. And again, it can take place also without a flame. That's typically referred to as glowing or smoldering combustion. Think about charcoal in a barbecue. So the charcoal typically is burning as this red glow without the presence of a flame. And so you have basically the combustion is taking place inside the charcoal, the solid charcoal itself, with oxygen from air that gets absorbed at the surface or in the depth of the charcoal. So this combustion mode is important. And in fact, very often in a wildland fire problem, we have both flaming and non-flaming combustion mode. And here I'm borrowing a movie that I took from Dr. Mark Finney, where you can look at an experiment over a fuel bed here. This is a top view on an inclined surface that has some kind of representative vegetation bed. And you can see the flame is propagating from right to left. And you can see here the flame that is going to move from right to left. And that, I would say, that flame is interesting, but is not unexpected. But in addition to this flame, you should be able to see a zone that is behind the flame that has this yellow glow. So you have the flame that is transforming your virgin biomass vegetation into flammable gases, and you have also the production of char, and that char can also burn in a non-flaming mode, in a smoldering mode, and that is identified by this red glow here in the movie. And finally, when the char oxidation reaction is complete, you are left with ashes. Okay. So if you are burning a log of wood in your fireplace, this is something that should be familiar to you. You are going to have a flame around the log of wood for some time, and then the flame will die, and then you're going to be left with a red glow that is corresponding to the smoldering combustion. And when you come back the next morning, you are going to find ashes in your fireplace, and so these reactions takes place sequentially in time or simultaneously as shown here, but both combustion modes are important to while on fire spread. So again, I'm going to talk mostly about flaming combustion from now on. So the structure of the flame can take a different form in the combustion literature depending on how the fuel and air are transported to the flame zone. And so if you go back to the Bunsen burner configuration that are typically the Bunsen burner experiments are typically presented to high school students in the US. In the Bunsen burner, you have a fuel that comes up to a tube and is going to be delivered with or without the presence of air inside the tube. So typically at the base of the Bunsen burner, you have orifices, one or two, and these orifices can be either open as here or closed. When they are open, they are going to allow the injection of surrounding air into the tube due to the Venturi effect. And then inside the tube, you have a mixture of fuel and air. If the tube is long enough, then this mixture is perfect, is homogeneous. And then basically, you have a flame that is supplied with a well-mixed stream of fuel and air that have been premixed prior to entering the flame zone. So this is premixed combustion. And these combustion events are not the dominant event in wildland fires, but they are responsible for some aspects of wildland fires. In particular, premixed combustion is important for ignition. And then you have the more classical viewpoint of a diffusion flame, where now the orifices at the base of the tubes are closed, so the tube only contains fuel. And the flame is going now to be at the interface of the incoming fuel from the tube and the surrounding air that is entrained into the flame zone due to buoyancy. And the flame basically is going to be at the interface of these two streams. So in that configuration, fuel and air remain segregated before entering the flame zone. And in fact, what's going to control the structure of this flame is going to be the mixing process between fuel and air. So two configurations for gas combustion that are quite different and controlled by different physics, and that's a classical viewpoint in the combustion literature. So in addition, let's talk now about non-premixed flames from now on. These non-premixed flames, they can also be differentiated according to the effect of buoyancy, and so our flames typically are dominated by buoyancy in fires, and to characterize the effect of buoyancy, we typically introduce a Froude number. So a Froude number is a characteristic velocity that represents the velocity of the flammable vapors as they are injected into the flame zone, divided by a characteristic velocity for buoyancy. So when you study buoyancy, the velocity always scales like square root of g, the magnitude of the gravity vector, times the length scale, and times maybe a delta t over t. And so that length scale can take different forms. Here I'm using the flame height as a relevant length scale. It doesn't really matter at the level of this slide, but basically this Froude number introduced here measures the relative weight or momentum compared to buoyancy. So in engine fuels, you have high momentums. The fuel is injected into an engine at several tens of meters per second, whereas in a fire, the flammable vapors that are released by the thermal degradation process that Dr. Stolarov talked about are released at velocities that are a few millimeters per second up to 1 centimeter or a few centimeters per second max. Okay. So very different situation. And the fact that we get flow velocities of meters per second scale is due to the acceleration of buoyancy. So we are in the regime where the Froude number is very low, and we are dominated by buoyancy in fires. And finally, you have to ask yourself this question, is the flow laminar or turbulent? So typically you answer that question by introducing a Reynolds number. So the Reynolds number is a characteristic velocity. Again, I'm taking a representative expression for a buoyant velocity here, times the characteristic length scale. And again, I'm using the flame height as my characteristic length scale for convenience, divided by kinematic viscosity. So at low values of the Reynolds number, you can have a laminar flame experiment. At high values of the Reynolds number, you are becoming turbulent. And and this differentiation is important. In a laminar flow, you are dominated by diffusive processes. In a turbulent flow, you are dominated by convective processes. So this is not the same thing. So in our fires, typically the Reynolds number are not that high, but they are high enough to be turbulent. So we have moderate turbulent conditions in fires, and we belong to the picture, the regime described by the picture on the right. And finally, in this introduction section, I want to say that the flame, especially diffusion flames, are quite sensitive to their environment. They are going to be sensitive to the way air is entrained into the flame zone. And so most of what I'm going to say in this presentation applies to flames that are going to be considered on flat terrain with no crosswind. But the situation where the flame is on a sloped terrain or with the presence of a crosswind is more practical, is of interest. So let me just say a few words here, and maybe I have a couple of comments coming down the line as well, but again, I will stay away from this. So here you can see that you have two limiting regimes that are introduced in the literature. You may already have heard this morning. There's a plume-dominated regime and a wind-driven or slope-driven regime. In a plume-dominated regime, you have a situation where the flame is essentially vertical, okay, and controlled by buoyancy. This flame is detached from the ground surface where you have the fuel from the biomass vegetation. In contrast to that, when you have enough cross flow, or when the flame is on a terrain that has a high enough slope, you're going to be in a situation where the asymmetry of entrainment into the flame is going to force the flame to be now a boundary layer flame that is attached to the ground surface, that is going to be horizontal if the ground surface is horizontal, or is going to be attached to that surface in case of slope terrain. And that's a very different flame geometry. So the exact geometry of the flame, whether it's vertical, detached from the ground surface, or attached to the ground surface, is quite different. The rate of spread of these flames are going to be quite different, and that's an important aspect of the combustion process for these flames. So the exact flame geometry, shape, and heat release rate and rate of spread depends on whether the flame is vertical or horizontal attached to a surface. And here I will only evoke these issues. I don't have the time to go into the details, but that's an important aspect. So in conclusion, if I want to describe here in this introduction section the structure of a flame, of a diffusion flame, I'm going to say, well, so the flammable vapors are produced by pyrolysis, by thermal degradation of an assumed solid fuel. This thermal degradation process requires temperatures that are typically on the order of at least 300 degrees C, so let's say 600 degrees K. So this piece of wood here, this wooden table, is not a hazard. I take the same wood at 300 degrees C, 600 K, then I'm going to start generating flammable vapors, and I have a fire hazard. The fuel that is now in vapor form emitted by thermal degradation is going to mix with ambient air, and assuming an ignition source is going to burn in a diffusion flame mode. And the temperature, the peak temperature of the flame is typically 1800 K, 2000 K in our flame. So if I take a candle flame and I do a temperature profile across the candle flame, somewhere in that profile across the flame, I'm going to see a peak temperature of about 1800 to 2000 K. Okay, so these are the typical maximum temperature that you expect in a fire. So the flame is non-premix, and as I pointed out, the flame is controlled by buoyancy because the release of these flammable vapors takes place at very slow velocities. Okay, and the flames tend to be turbulent because the Reynolds number is high enough, typically not because of high velocities, but it's high enough because of larger length scales in our problems. All right, so that's an introduction. So let's talk a little bit more about the coupling between pyrolysis and combustion. Again, pyrolysis is the production of the fuel. Combustion is the production of the heat. And Dr. Soliarov already described this. You have basically heat that corresponds to exchange of information from the gas to the solid So the gas is where combustion takes place, and some of that heat released by combustion is going to go back to the solid, and the solid in return is going to provide the fuel that the flame needs, that the combustion process needs to be sustained. I actually like to present this as a thermal feedback loop process, and so I like these diagrams that show the coupling between pyrolysis and combustion. So bear with me on this. So let's start, for example, let's assume that we have a certain amount of flammable vapors generated by a piece of wood that is thermally degrading. This fuel is going to mix with ambient air and burn. Let's assume that we have an ignition source. The burning process is going to release a large amount of heat, and now we have high temperatures in the flame region. And when you have high temperatures, you're going to have heat transfer. And so we have a fraction of that heat that is going to go back to the fuel source through convective and radiative heat transfer. This is what we call the thermal feedback, the heat feedback. So a fraction of the heat generated by combustion goes back to the fuel source, which is a key because the process of phase change that is described by pyrolysis is endothermic globally. Okay, this is the same thing as evaporation of liquids. You need to provide energy for this phase change to occur. So this heat that is coming back to the solid is going to be required to sustain or even amplify the burning process. So typically in undergraduate heat transfer, you typically come up with expressions that look like this. Typically in the context of evaporation, if you look at the evaporation of water, you're going to say, well, let's look at the rate of heat transfer that goes back to a surface of water, okay? And that's in units, that's a heat flux in units of kilowatt per meter square of the pool of water surface. Assuming that all of this heat is used for evaporation, you can have the rate of evaporation here in units of kilogram per second per meter square. So the mass rate of evaporation of water in my example, times the heat of evaporation of water, that is going to be the way the liquid water is going to use the incoming heat to evaporate the water. So this is a very simple heat balance statement that is only an approximation in the case of pyrolysis processes, but is good enough to show the strong coupling that we have between the heat transfer measured by the heat flux and the release of flammable vapors, the release of fuel from the combustion process. So everything is heat driven. So the pyrolysis is heat driven. So I can look at the simplified statement again for just to guide it's qualitative rather than quantitative. So you can write that the rate of pyrolysis per unit meter square of exposed solid fuel surface area is equal to the net heat flux due to convection and radiation heat transfer divided by a heat of pyrolysis, or this heat of gasification that Dr. Solarov had introduced, that measures the heat that you need to provide to vaporize 1 kilogram of fuel. So, and you can integrate this over the entire surface area of your fuel. So basically here you have a quantity that is typically described in the literature as the mass loss rate, which is the amount of mass of fuel that you produce per unit time due to pyrolysis processes in units of kilogram per second. And on the right-hand side, you show that the mass loss rate is equal to the rate of heat transfer in units of watt divided by the heat of pyrolysis. Okay, so again, the thermal feedback controls the mass loss rate. All right. What about the heat of combustion? The heat release rate. The heat release rate is going to basically follow the fuel. So once this fuel is released by thermal degradation processes, and assuming that we have enough oxygen to consume all of that fuel for combustion, that's an overventilated fire condition assumption, which for wildland fires is usually adequate. So you can say that the rate of heat release due to the combustion process in units of watt is equal to the mass loss rate times the heat of combustion, which is the energy released by 1 kilogram of fuel every time it finds the oxygen that it needs and burns through a combustion process. So you can write that the heat release rate is equal to the mass loss rate times the heat of combustion. Okay, and that's a very important relationship that is true in an average sense that shows the relationship between the rate of pyrolysis measured by MLR, by the mass loss rate, and the rate of combustion measured by HRR, the rate, the heat release rate. All right. All of this is nice, but of course, the relationship between the thermal feedback and the mass loss rate is more complex than what I described. So this is actually my take on pyrolysis processes. It's less detailed than what Dr. Stolyarov does, but this is the kind of thing we are trying to put in our models. So we have to account for moisture inside the fuel. So we have a drying reaction. So we have a wet solid that can be turned at a temperature close to 100 degrees C, roughly, into water vapor and a dry solid. And that's an important step because this step is greatly endothermic, and that explains why higher contents of moisture in biomass vegetation are going to be basically correspond to lower temperatures and a lower probability to spread the fire. Then the second step, described here by two reactions, is a step that corresponds to the true pyrolysis processes, where you take the dry solid and you transform that dry solid into fuel in the gas phase available for the combustion process, and a solid residue that we call char. This was this char identified by the red glow in the movie from the Missoula Fire Sciences Laboratory. Okay. One of these reactions requires oxygen, the other does not, but let's stay away from this discussion here. And then finally, you have the char that can also release heat. The reason why the char has this red glow, it's because it's actually burning like the charcoal in a barbecue, and but it requires oxygen, and it's going to lead to combustion products. They can be CO, CO2, they can be complex in chemical composition, but let's stay away from that. And finally, a solid residue at the end of this process that we call ash. One important aspect in this description is that the pyrolysis process is typically endothermic, but the char oxidation process, the last step in this slide, is actually strongly exothermic. So you can have a situation where the glowing reaction, the smoldering reaction, can be self-sustained because it can generate its own heat. Okay, and you're going to see Professor Guillermo Ren talk about this tomorrow morning. So as mentioned by Dr. Stolyarov, you have a lot of parameters in this model when these models are available, and the question becomes, how do you optimize these models? So he talked about this, so I don't have to go into the details. So you have a number of experiments that are available to parameterize and calibrate these models when you have a mathematical model, and calibrate the parameters when you have a mathematical model. So you have macro scale experiments that basically consider thermally thin samples. You have bench scale experiments that correspond to thermally thick samples. And you have also experiments, as shown here, that are going to burn the real thing. Okay. Full-scale experiments looking at fuel packages that are representative of the biomass in the field. So all of these viewpoints, of course, bring useful information in our understanding of the physics as well as in model development. I'm a modeler, so I tend to view the world through mathematical equations and computer algorithms, so bear with me on this. So I want to add something to what Dr. Stolyarov has said, to illustrate what, to me, pyrolysis is. So here, this is a simulation of an experiment that was performed some years ago, I think at Nice, and using a model that was developed by Chris Lautenberger and Carlos Fernandez-Peyo at Berkeley. So you have a piece of pine wood here that is 3.8 centimeter thick, 10 by 10 centimeter in a cone calorimeter experiment that is exposed to a radiant panel that is 40 kilowatt per meter square and on the normal air. And you are looking at the thermal degradation of this piece of wood. And you can see we are looking at a 10 minutes timeline here. So you can measure the mass loss rate in units of kilogram per second, or if you divide by the 10 by 10 centimeter square surface area in units of kilogram per second per meter square. And you have a curve that looks like this. So typically, the mass loss rate after a very short ignition delay here, the mass loss rate is going to take positive values, are going to go for a peak. The initial increase is due to the fact that you are bringing heat to your sample, and this sample is going to start thermally degrading. So you produce flammable vapors. You trigger that phase change that produce fuel to the gas phase. And then the subsequent decrease typically is associated with the formation of a char layer that is going to allow the pyrolysis reaction to go in the depth of the sample, but it's going to be harder for the pyrolysis process to do its job because it's going to be deeper inside the sample and it's going to be protected, insulated from the outside heat flux because of the presence of a char layer. So all of this is well known and well characterized in the literature. What I want to look at is what's happening inside a sample at a given time. This is again a simulation, it's a model, but that model has been calibrated with success to experimental data. And I like to use this model to give me insight into the physics. So here you have a temperature profile at a given time, let's say 100 seconds, why not? And you are looking at temperature as a function of distance inside the sample. So here x equals 0 correspond to the back surface of the sample, x equal 3.8 centimeter correspond to the exposed surface. So you have heat coming from your right to the left in that diagram. So not surprisingly, if you look at temperature, you expect temperature to be high on the right-hand side of that plot because this is where the heat is coming, and that heat is slowly diffusing inside the sample. Okay. All right, so that picture is, I think, is what we might expect. If I look now at what's happening in terms of chemical species inside that sample, so here you have the dry solid. You have the wet solid. Here you have the dry solid, and the region where the dashed black line is changing into a solid black line means it's the region where you have evaporation of the moisture. And then you have the red solid that corresponds to the char, and finally the blue solid that corresponds to the ash. So you see there are a lot of things happening inside at this time, happening inside that sample. You have a core that is unaffected yet, and you have things that are happening at the surface, but over time things are going to move from the surface to the interior of that particle if you maintain the 40 kilowatt per meter square external heat flux. All right. Here I have a description of the reaction rate. So the black line is the evaporation rate. The red lines correspond to the rate of pyrolysis, and this small peak here corresponds to the rate of char oxidation. The point I want to make is a point that was the main reason I wanted to show these slides, is that first of all, it's important to have this insight of what's happening inside the biomass, okay, and also look at the length scale over which these changes are occurring. This is millimeter scale, okay. So that means that there's a lot of detail of the physics and chemistry occurring at very small length scale inside the solid biomass. And numerically, that means it's pretty challenging to actually describe and keep up with these processes as they occur. And these processes are responsible for the production of fuel. And the production of fuel is responsible for the heat release rate of the fire, which is the most important quantity in a combustion problem. So you can see that how things get together and why our problem is complex. You're going to have this week people who are going to talk to you about the large length scales, okay, the tens or hundreds of meters, maybe kilometer scale, the aspect of the fire dynamics. And these global scales, these larger scales are very important. But also, at the end of the day, for me, things occurring at the millimeter or centimeter scale, certainly at the meter scale of the flame, are important processes that are responsible for the heat release, for the production of fuel, and for the spread of the fire. So one of the difficulties that we have as a community is to put all these things together. I think it's Dr. Simeoni this morning says that there is nothing really new about the physics that we are studying. It is true we understand somewhat the pyrolysis. The pyrolysis is still difficult, but we certainly understand the fluid mechanics, the combustion, the radiation heat transfer. We make great progress on these disciplines. But the coupling between all these phenomena is the difficulty. We still do not understand the spread of a fire because we don't really understand how these different pieces of the physics are coupled together. All right. So here I'm going to go a little bit faster because I think many of you may have seen this, and so and I need to keep an eye on time. And so The global combustion equation viewpoint is a very useful viewpoint, even though it has some limitations. And in that viewpoint, you consider the combustion process as a black box. So you're looking at what enters the black box. You have air and fuel that has been released maybe by a pyrolysis processes of a solid fuel. And you have the products that are typically carbon dioxide and water vapor. And that viewpoint is usually powerful enough for us to describe the combustion process. So in the combustion literature, this viewpoint can be written. You write a global combustion equation, which is a conservation of mass statement, or sometimes also described as a combustion of energy statement. So you can write it as per unit mole of fuel basis or per unit kilogram of fuel basis. Usually I prefer the second viewpoint because what is conserved is mass, not number of moles. But usually the literature prefer the first viewpoint. So you can write the coefficients that appear in this equation, and I will not do it here. This is classical combustion textbook presentation, but you can write these coefficients based on the idea that combustion is going to conserve mass. So if you have 1 kilogram of reactants, you end up with 1 kilogram of products. And more than that, combustion is going to conserve the mass of carbon, hydrogen, oxygen, and nitrogen. Combustion is going to break the molecules, but it doesn't break the atoms. Okay, we're not going to do nuclear physics in combustion. So you break the molecules, but you don't break the atoms. If you don't break the atoms, you have as many number of carbon atoms on the left-hand side of this statement as you have on the right-hand side. And you can repeat that statement for oxygen, nitrogen, and hydrogen. And that gives you basically constraints to calculate the coefficients in this equation. So I'm going to go a little bit faster on this. One aspect that is important in this equation, I said it's a conservation of mass statement, but it's also a conservation of energy statement. You can look at the heat of combustion, which is the heat released by when you burn 1 kilogram of fuel. You can look at the heat of combustion as being a difference in the heat of formation for the reactants, between the reactants and the products. So technically, that's what you learn in a combustion course. Typically, we don't need to go to that level of detail because we look at this global combustion equation as a model rather than a description of the true changes in chemistry that typically involves tens of chemical species and hundreds of chemical reactions. So we typically view it in a more empirical way. We can write that the heat of combustion, the heat release in units of joule per unit kilogram of fuel consumed, as a stoichiometric coefficient R sub S that appears in this equation times the heat release, the heat of combustion per unit mass of oxygen. So this is the amount of heat release every time you burn 1 kilogram of oxygen, and this is the heat release every time you burn 1 kilogram of fuel, and R sub S is just the stoichiometric oxygen to fuel mass ratio, or this oxygen to fuel mass ratio that you find in this equation. And it turns out that in the literature, you can find that a good estimate of the heat of combustion per unit mass of oxygen, independent of what you burn, roughly speaking, is on the order of 13 megajoule per kilogram. So you can use this equation to show that when you are burning cellulose, for example, if you use this equation for cellulose, you're going to find the different coefficients that you need, and in particular R sub S, and you're going to find that the heat of combustion is on the order of 16 megajoule per kilogram, which is a representative number for the combustion of many biomass fuels. So there is a lot of good information coming from the simplified viewpoint, this thermodynamic viewpoint associated with the global combustion equation. In addition to this equation is going to give you some understanding of over and under ventilated conditions. So up to now, I've written this global combustion equation with conservation of mass statements and conservation of number of carbon, hydrogen, and oxygen atoms on both sides. And the coefficients I get out of this analysis are called stoichiometric coefficient. They correspond to an optimum, to stoichiometric proportions on fuel and air. That is an optimum from a chemical standpoint. Okay, it corresponds to maximum temperature, maximum heat release for the combustion process, and maximum yield of CO2 and water vapor. So the question becomes, okay, what happens if I'm not at this optimum? Well, to be able to answer that question, you need to have a control volume analysis. So you're going to give yourself a control volume, and you're going to look at the number of mole of fuel that you have under initial conditions. The superscript I means initial state, and the number of mole of oxygen that you have in this control volume, assuming a well-mixed mixture of fuel and oxygen, prior to burning. So you can introduce the equivalence ratio, which is going to be a non-dimensional fuel-to-oxygen mole ratio under those conditions prior to burning, made non-dimensional by the same ratio taken under the stoichiometric optimized condition. Okay, and that stoichiometry, this in my notation is 1/nu02. So the point here, this is basically a measure of the fuel-to-oxygen ratio as a mole ratio or mass ratio, it doesn't matter, taken under conditions prior to burning. And that will allow you, after that, that's not what I wanted to do. This will allow you now to look at a wider range of problems with ease. You can say, what in my control volume, I can have two conditions. This parameter phi, this global equivalence ratio, can take values below 1 or above 1. So the regime of values below 1 means now that we have NF over NO2 that tends to be small. That means that we have more oxygen than required by the combustion chemistry. So we're going to have plenty of oxygen to completely oxidize the fuel present inside the control volume. This is the overventilated regime. Okay. Under this condition, the combustion process will burn all the fuel and will leave some excess oxygen in the combustion products. And you can rewrite your global combustion equation to represent this, and this is an extending combustion equation that applies to the phi smaller than 1 regime, where you can see on the right-hand side the presence of excess oxygen. All right, and you can do the same for the similar regime of underventilated combustion, a situation where NF over NO2 takes large values. So now you're in a situation where you don't have enough oxygen to completely burn, completely oxidize all the fuel present in your control volume. And in that case, you're going to be left with excess fuel after the combustion process has completed. Okay, and this is reflected by this combustion equation. So this combustion equation, again, can be adapted. Usually it's written in textbooks for stoichiometric conditions, but you can extend it and apply it to this fuel-in or fuel-rich regime and describe that way the effect of under or overventilation. The true physics or the true chemistry is more complex than described by this black box model of the global combustion equation. And we know that under high temperatures, CO2 and H2O are not going to be the only products of combustion. We're going to find tens of chemical species in the combustion products. And in particular, we're going to have some minor species listed here. And also the excess fuel that you have in the underventilated combustion regime is not going to remain as a virgin fuel. It's going to break up into products of incomplete combustion like carbon monoxide, hydrogen, hydrocarbons, and large amounts of soot typically. So typically this global combustion model actually works pretty well for well-ventilated conditions, overventilated conditions, and start to lose accuracy when you go to the overventilated regime, the underventilated regime. So this model is actually very good for qualitative analysis, but lacks quantitative accuracy, especially in the underventilated combustion conditions. So to be able to describe that, typically in the combustion literature, you have to use software, so they specialized software to calculate the composition of chemical products. So here, this is an example of a calculation done with Kenkin, where you have the products of a methane air combustion process on the normal temperature and pressure conditions. And on the x-axis, you have the equivalence ratio. This line here corresponds to phi equal 1. And you can see that on the left-hand side, for phi smaller than 1, you have the overventilated regime. You can see that you have the blue line corresponds to excess oxygen present in the product stream. Similarly, when you go to the right of this phi equal 1 line, you're going to find that you have some excess fuel. This excess fuel is calculated not as being in the form of methane, but it's going to be carbon monoxide and hydrogen. Okay. So this is well characterized by these pieces of software that shows that the chemistry is more complex than the one that is assumed in the global combustion equation. But the global combustion equation model is still pretty successful at showing that the products are maximum close to stoichiometry. Not exactly at stoichiometry here for this dashed line that is water vapor, but close to it. So that's a pretty good qualitative description of the fact that you get maximum yield of the combustion products at stoichiometry. If I look at temperature, and this same software can calculate the flame temperature again takes a peak value at phi equal 1. So you can see that the global combustion model is successful at describing a lot of the most important features of combustion process. They even provide here, these pieces of software provide an estimate of the flame temperature. These flame temperatures are higher than 2000 K because radiation losses are neglected here. If you take into account radiation, typically your flame temperatures are going to be on the order of 2000 K. All right. Let me keep going. A little bit about chemistry. I won't say much, just to say that most of the time we don't need chemistry, which is, I guess, good news. I mean, for some of us at least. One of the things that in a global combustion model, the thermodynamic viewpoint, you are describing the composition of the products as a function of the composition of the reactants for given temperature and pressure thermodynamic conditions. But you're not giving any information about how fast the combustion takes place. So to have some information on the speed of combustion, you need to do chemical kinetics. That's the chemistry viewpoint, or you need to do flame analysis. That's the mechanical engineering viewpoints where chemistry is coupled with diffusive transport, convective transport of chemical species. Let's look at the viewpoint of chemistry here first. And so chemistry looks at a mixed mixture of fuel and air, and is going to try to describe the evolution of that mixture as a function of, let's say, temperature. Let's assume that we are atmospheric pressure to simplify. And so the most fundamental way of looking at it from a combustion chemistry viewpoint is to look at the rate of change of a reaction at the level of an elementary reaction. So elementary reaction in chemistry means that this is a reaction that tries to describe true collisions between molecules. This is the quantum chemistry viewpoint. This is the most fundamental viewpoint that we have available to us. And that's a high fidelity viewpoint. Okay. Now, this is the viewpoint of the kinetic theory of gases. And in that theory, you're going to write that the rate, and not going into some of the details, the rate of chemical change associated with this particular elementary reaction is related to the frequency of collisions between the molecule R1 and the molecule R2, which typically we describe as the product of the concentration of R1 times the concentration of R2, times a term here that is very important and temperature dependent that measures the probability of success of a collision. Success here being defined as leading to a chemical change to products. Okay. And that's the beginning of the Arrhenius model. So in fact, the full Arrhenius model, I guess, coming in the next slide, or I can even go, well, no, let me take a step back. So in the Arrhenius model, the probability of success of collisions is described by this reaction factor that typically involves a pre-exponential factor, sometimes a temperature exponent, most of the time in the combustion literature, and an activation energy that measures the sensitivity of this factor to temperature changes, because really the most dominant term is this one. So this term is responsible for saying that at ambient temperature, if I release methane in this room and methane mixes with air, at ambient temperature, the risk is pretty low of anything happening. So this term will be close to zero. But if I raise the temperature to a few hundreds degrees C, then this reaction can start, and in that case, it's going to be very fast. So you have to have a binary dynamics in combustion system where either nothing happens or everything happens super fast. Okay, it's one or the other. So, and that's the exponential dependence on temperature that is responsible for this. So that's a feature of combustion processes. So Well, I don't need to go there, so let me gain a little bit of time by going there. So if I plot the exponential term that is part of the Arrhenius model versus temperature, and here I'm trying to graphically represent what I just said, I find that basically the term at low temperatures below 1000 K, roughly speaking, is exponentially small to the point that it's close enough to zero, we can consider that it's zero. Again, if I remove methane and allow methane to mix with air in this room at 20 degrees C, 300 K, nothing is happening because this exponential term is so low that there is no hazard. So the chemists say that the mixture is frozen, okay, which means that the chemistry is infinitely slow. On the other hand, at temperatures above 1000 K, roughly speaking, I can get a term that gets exponentially high and it's going to be super fast. So again, these binary features due to the Arrhenius chemistry and due to this exponential term is very strong. Again, the Arrhenius chemistry is based on solid ground for gas phase combustion. This is the kinetic theory of gases. This is based on quantum chemistry. This is the best we know in terms of these combustion transformations. So let me move on to this and start going now to the flame problem. Okay, moving from the chemistry to the flame. So first of all, the fact that the chemistry is very fast means that the flame is going to be very thin. Okay, the typical thickness of a flame defined as a region where you release heat in a candle flame or in a turbulent diffusion flame, the thickness of the flame is typically on the order of a fraction of a millimeter. Okay, very thin. And the reason why it's thin is because chemistry is very fast. Okay, so this goes hand in hand. All right. The other practical aspect, and this important conclusion from this discussion, is that if chemistry is fast, maybe I can ignore it. Okay. So the combustion is basically can be viewed as a sequence of two steps. You take the fuel and you take the oxygen, and you have to bring in the fuel and oxygen to the region where it's hot when it can react. So they have to meet, and they have to meet with some heat. Okay. So there is a transport, a mechanical step associated with transporting the fuel and the oxygen to the flame. And then there is a chemical step where the fuel and oxygen meet, they shake hands, and they transform into CO2 and H2O. Okay. But that second step is super fast. Okay, because under normal conditions, the chemistry is very fast. So you're going to be basically rate limited by the fact that you have to transport the fuel and oxygen to the flame. This is why these flames are described as diffusion flames. We call them diffusion flames because they are limited by the diffusion of fuel and oxygen to the flame zone, and the chemistry can be ignored. Okay. Again, I made some qualification to that statement earlier on. I'm not going back to that. But under normal circumstances, when the flame is established, you can forget about chemistry as far as the heat release rate or the flame structure is concerned. So that also means that if I want to describe the flame structure, when you go to the combustion science literature, you really have to describe the flame structure in terms of a mixing variable. That's the mixture fraction. I'm not going to say much about the mixture fraction. I don't have the time. But the mixture fraction is defined as the local fraction of mass that comes from the fuel stream and takes the value of 1 in the fuel stream and the value of 0 in ambient air. And I will leave it there for this. But it's a way basically to describe the mixing process between fuel and air. And the reason why this variable is so important, it is because this is what is controlling the structure and the rate of burning of these flames. So you have this viewpoint that is a little bit simplified, but is good enough to really understand the structure of laminar or turbulent diffusion flames. I should say that turbulent diffusion flames typically are described as a collection of laminar flames. So when you understand a laminar flame, you also understand much of the story about a turbulent flame. A turbulent flame can be viewed as a flame that is distorted, wrinkled by convective motions, but if you zoom on a piece of a turbulent flame, it looks like a laminar flame. So basically, the description of laminar or turbulent diffusion flames is based on an understanding of the effect of mixture fraction. So you basically have two regions in these flames. Well, you have two regions separated by a thin interface, which is the flame. Again, this idea that if the chemistry is infinitely fast, when fuel and oxygen meet at the red line here, they are instantaneously transformed into CO2 and water vapor, and you release heat. So you have two regions. You have in this simplified model, you have the fuel side of the flame. That is a region where you're going to find combustion products are going to mix with fuel. But one important aspect is that there is no oxygen there. Okay? Dr. Solarov mentioned that he is sometimes in his analysis considering that there is no oxygen on the fuel surface. And that's consistent with this infinitely fast chemistry viewpoint of diffusion flame. All the oxygen that is trying to be diffusing towards the flame, as soon as it arrives at the flame and meets some fuel, is going to be transformed into products. So there is no mechanism for this oxygen to leak into the fuel side of the flame. Similarly, when I look at the air side of the flame, I find combustion products, CO2 and H2O, mixed with ambient air. But I don't find any fuel because all the fuel that is coming from the fuel side is going to be entirely consumed at the wet surface. So you have this impermeable surface that is not going to allow fuel and oxygen leakage across the flame because of the assumption of infinitely fast chemistry. So that's the Burke-Schumann model. The Burke-Schumann model is really the fundamental building block to understand the structure of laminar diffusion flame or turbulent diffusion flames. It has some simplifications, but this is still the starting point of insights and analysis and also models. So in this model, basically you can describe the entire mixture composition as a function of mixture fraction. The flame location is given by a certain value, a stoichiometric value of mixture fraction. And you have oxygen on one side of the flame, so this is the air side of the flame, and you have fuel on the other side, this is the fuel side of the flame. And I'm not going into the details, but this is really, if you want to understand the structure of these flames, this is where you need to start. There is also a description on the adiabatic conditions about the heat distribution across the flame as a function of mixture fraction. So, I'm going to keep moving on, looking at the characteristic length scale of the problem, which is the flame height. So, the flame height in a diffusion flame is the main characteristic length scale that is used for characterization of the flame behavior. In the buoyancy control regime, the literature says that the flame height scales with a full number to the power 2/5 or to the power 0.4. And the full number can be written in different ways. Here it's written a little bit differently from the expression I had a few slides ago. So this is a representative value of the flow of the fuel velocity as it is released from the burning surfaces due to pyrolysis. And here I have a buoyant velocity that is square root of g times an estimate of the size of the fuel source as opposed to an estimate of the flame height. So bear with me on this, but this is one of the many ways of introducing a full number. And the literature shows that the flame height scales with the full number to the power 0.4 for pool fire configurations. So in the fire protection engineering literature, actually people don't like to use full number. I don't know why. They went their own way. So if you go to the combustion science literature, you have a full number. If you go to the fire protection engineering literature, you find a Q star parameter that I think originally was introduced by Elzukowski at Caltech. And this looks like a non-dimensional heat release rate. You can show that this Q star parameter is actually roughly proportional to a full number. So you can talk about Q star or talk about full number, you're talking about the same thing. And you can go to the fire protection engineering literature and you find correlations that gives you the flame height. Here, this is non-dimensional flame height, made non-dimensional by an estimate of the size of the fuel source area, as a function of Q star to the power 2/5 that you can read as full number to the power 0.4. And so this is a correlation that is valid in the buoyancy dominated regime for values of this Q star parameter up to 10 to the power 5, which is very large, much larger than anything we worry about in fire application, and down to a number about 0.1 or 1. If you go below Q star below 0.1, you are in an unusual circumstances of fires that are so distributed in size that they look like what people refer to as mass fire. And these mass fire are very large pool fires that you can find sometimes in industry. And these fires typically have a special geometry because instead of having a single conical shaped flame, you have multiple flames due to buoyant instabilities. And so the flame transition into a different geometry when you go to very low values of Q star. But let me stay away from this. So this is a correlation that is valid for pool fire over a large range. Something that I don't have a lot of time to describe, so I'm trying to decide. I'll describe it in passing, to make an important point. So something that you find in the literature for pool fires, and you have a similar literature for line fires I will review in passing in a few slides, is that you have a description of the variations of quantities of interest, like the vertical velocity or the temperature of your flame or your plume as a function of elevation. And usually the starting point is a far field theory where your flame is considered as a point. So you are far from the flame. And you can look at the variations of these quantities, vertical velocity or temperature as a function of elevation. And when in this analysis, you have to introduce a horizontal velocity that is the air entrainment velocity. And it's very important to understand mechanistically, I mean, people who are doing flame mechanics shouldn't be surprised that when you have strong buoyant acceleration in vertical direction, you must have some horizontal motion and bring air into your flame or your plume. This is, you can call it air entrainment. This is also at larger scale what is called a fire-induced wind. Okay, the fact that this is the direct result of buoyant acceleration. So you're going to have entrain air from the surrounding into the flame or into the plume zone as a result of buoyant acceleration. And these theories describe the influence of this air entrainment process. So this is an important point. I think I'm going to stay away from these details because these are engineering correlations. Like any academic person, I speak too much and trying to, be aware of your time. And and you can also conduct the same kind of analysis by looking at a line fire, which is a simplified representation of a one-on fires that spreads linearly in a certain direction. So here, when you are looking at the line fire problem, you have, instead of looking at the heat release rate, you're going to look at the heat release rate per unit length of the fire line that you assume infinite. And so the right quantity is the fire intensity in units of watt per meter of the fire line. And you can have estimates of the flame height. Again, the flame height is very important. That's your characteristic length scale of the problem. And so you're going to have estimates of your flame height as a function of now the fire line intensity. So you see all these correlations are available to characterize the flame height as a function of the heat release rate in a pool fire configuration or the fire line intensity in a line fire configuration. This is important. This is used in many ways. For example, there are a lot of techniques that would like to estimate the heat release rate that is very hard to measure and typically we cannot measure. So if you look at the flame height, you can invert this relationship and estimate what the heat release rate is. Okay, so there is a lot of value in making sure these correlations mean something and are accurate. So also, what are the typical values of the heat release rate or the fire line intensities in fires? Well, the heat release rate, Q dot fire for a pool fire configuration is typically going to be on the order of, let's say, a few hundreds kilowatt. Bear with me on this writing. Hundreds kilowatt per meter square. It depends on what you're burning, but a representative value is, if I'm burning this table, I'm going to say, roughly speaking, this is 100 kilowatt per meter square of table. This is a typical value. Okay, I may be off by a factor that I can make more accurate if I know exactly the composition of the table. Similarly, when I look in the one-on fires, Q dot prime fire, if I'm burning in the lab, typically the values of the fire intensity are a few hundreds kilowatt per meter. If I'm doing a prescribed fire, typically I have values between 1 and 10 megawatt per meter. And if I'm looking at mega fires, extreme events as described this morning by Alex Filkoff and Albert Simeoni, I may be above 10 megawatt per meter. This is a kind of range where you say this fire is so huge, there's no way you can suppress it and you better run from it. So These values are important to have in mind. Again, there is always per meter or per meter square analysis. That is, you need to tell me, to have the total heat release rate, you need to tell me what is the length of your fire line, or if you are looking at a pool fire, you tell me what the surface area of the pool fire to get a number in units of watt. All right, so again, I'm going to... Okay. I'm trying to make strategic decisions on how much I want to say from here. One important aspect about the physics, that's something, I don't know, I'm going to say it because it's important, is that one question, and going back to this equivalence ratio, I can define the control volume as being the flame. Okay, you can see that I can design a control volume around the flame in a wildfire problem or a structure fire problem. And the question I'm asking myself is, what is the equivalence ratio inside this control volume? Is the flame capable, it's going to create its own wind, is the flame capable of self-ventilation? Okay, that's not an easy question to answer until you look at the data. Well, so I can define phi through a theory, and then I have a little bit of a technical problem where the fuel to oxygen mole or mass ratio prior to burning, I don't know how to estimate this. And so there's a steady state assumption where you can replace a mole or mass ratio by a mole flow rate or mass flow rate ratio. And now you have here the mass loss rate, and here you have the rate of air entrainment into the flame zone. So there's a little bit of technical analysis associated with estimating these values of phi, but you can do it theoretically, or you can measure it in the lab. And it turns out that, roughly speaking, a fire on Earth is capable of entraining 10 times the amount of oxygen that it needs to burn. Okay? We are not lucky because, if we were in another planet with reduced gravity, then this number may be actually closer to 1. Okay, so less entrainment if gravity was not as powerful. So if you go to outer space, this number will go up. And if you have no gravity, then this fire will actually self-suffocate because of no air entrainment. Okay, so the fact that this number is low means that this flame is pretty healthy because it's capable of entraining by natural convection the air, and in fact 10 times the amount of air that it needs to burn. So that's an important aspect, I think, of the dynamics and structure of these flames. I want to bring an experiment that was performed also by Mark Finney and Sarah McAllister at the Missoula Fire Science Laboratory, where they were looking at wood cribs and look at the implication of this analysis, looking at wood cribs. So on the left, you have a wood crib that is on the floor, okay, and is capable of entraining air from the surrounding. And this amount of air for the amount of fuel inside of the wood crib is not enough, so this fire is actually underventilated, which means that the flame is sitting on the edges of the wood crib because the flame is always going to stabilize close to the stream of the deficient reactant. So if the flame requires more oxygen, it's going to look for it. Okay, we all do that in our lives. We always look for what we are missing. And so the flame is going to look for the oxygen and stabilize on the edges of the wood crib. Okay, that's the picture on the left. The picture on the right corresponds to an elevated wood crib. So now you have more entrainment because you have entrainment from the bottom surface of the wood crib. So this same wood crib is now much better, is better ventilated. Okay, and now you have overventilated conditions, and you can see that in the picture that now you have the flame structure has changed. You have individual flames stabilize around the individual wood sticks of the crib inside. Okay, because there's plenty of oxygen, and again the flame is going to say, well, I need plenty of oxygen, now I need the fuel. So he, I don't know what the sex or the gender of it. My French is coming to we say la flamme in French, so bear with me on that. So the flame is going to stabilize close to the fuel surface. And the thing that you're going to, you may see, oh, it's anecdotal. It's not anecdotal. You can see the luminosity of the flame is not the same for the two pictures. So in fact, the right-hand side corresponds to a situation where the luminosity is higher. So the fact that the flames are now stabilized around the individual fuel sticks corresponds to a situation where there is more burning rate, more thermal feedback from the flame to the fuel surfaces, more burning rate, higher heat release rate. So it is the same fuel but just basically with different access to air. And so this concept of over and under ventilated, even though we are in a wildland fires and looks like globally we have plenty of oxygen around, they affect the structure of the flames and they're going to affect the burning rate as shown here. All right, so another point here, even though I said that the picture on the left is a picture where I've limited myself for this presentation. So a fire with no, on flat terrain with no crosswind. Okay. In that case, the flame and the plume are going to be vertical, and I have symmetric air entrainment. Okay. All right, so that's the textbook case. But now when you have wind, or when you have a slope, you're going to have asymmetry in the air entrainment, and the flame is going to be deflected. It's going to be deflected from upwind to downwind, or it's going to be deflected from downslope to upslope, okay, because of the blockage due to the slope. So you don't have the same amount of air entrainment on both sides of the flame because of these changes in the airflow or these changes in the topography of the terrain. And that has a big impact because now, depending on where the flame is, if the flame is propagating from left to right, then the thermal feedback is going to be favored in this wind situation or in this slope situation. So the effect can be positive or negative depending on the exact details of the configuration. But you can see that up to now I've limited myself to describing a nice vertical flame and pool fire, but the thermal feedback to the surrounding and the subsequent rate of pyrolysis rate and the subsequent heat release rate and the rate of spread are going to depend on these details. I want to show another example of that, picking up again on a study that was done at the University of Coimbra by Domingos Viegas and some of his students, Jorge Raposo. This study was also mentioned, I think, earlier by Albert Simeoni. This is the problem of the interaction between fires. If you want to understand the interaction between fires, you have to think air entrainment. So if I have two fires that are close enough to each other, then I'm going to create a situation where the fires cannot entrain any air from the in-between region because they are going to block the air entrainment process. And so the air entrainment process is going to become asymmetric, and the two fires are going to start bending toward each other because of the fact that there is no air to entrain in between. Okay? And so now, and that's what you see very clearly in the pictures, these flames are going to be deflected towards each other, and then you have now going to have in between regions a region that is going to receive higher levels, higher intensities of the thermal feedback, and it's going to lead to higher burning rate and a higher spread of the flame. So the merging of fires is another example of the importance of air entrainment and the sensitivity of diffusion flames to their environment. All right, so bear with me, I'm almost done, because what I have after that is something that belongs more to Sarah McAllister's presentation tomorrow. So this is a little bit of a repeat of some of the things that you've seen. I think repeat is not bad. Okay, we are all talking about the same physics for this problem, even though we may have slightly different perspectives. The question after that is, okay, you have a certain flame. This flame may have a geometry that depends on the environment. What is this flame doing to its surroundings? So the first thing that we are thinking about is flame spread. So the flame is going to thermally load the unburned biomass vegetation around it and spread the flame that way. So as already pointed out by a number of presentations today, you have radiativity transfer, convectivity transfer, and firebrands. And I'm going to gladly just skip some of the details. So just mentioning in passive, when you're looking at radiation transfer, the critical criterion for the start of pyrolysis, or what we call ignition, the start of combustion or start of pyrolysis, is to have a radiative heat flux that is above a critical value that we call the critical heat flux. We mentioned it in the discussion session with Dr. Stolyarov, 10 kilowatt per meter square roughly for structure fires, or 30 kilowatt per meter square for fine fuels in a wildland fire application. These are, ballpark numbers. So you need to have a relative heat flux that is as high of these critical values if you want to create ignition due to radiation. And by the way, this analysis is part of the idea of a safe distance of defensible space. Okay, the idea that the forest has to be, 30 feet from your house in a wide non-urban area is based on analysis of this criteria. If you are looking, skip that. If you are looking at convectivity transfer, so convectivity transfer is basically the idea that when you are putting on-burn mass, solid mass, biomass vegetation in contact with hot gases, whether it's the flame or the plume, then if these gases are hot enough, you're going to lead also to enough heat transfer to start the pyrolysis processes. So roughly speaking, you want the gas to be above the critical temperature for pyrolysis that are estimated as 300 degrees C or 600 degrees K. So that's the criterion. You need to have gases in contact with unburned vegetation at a temperature above 600 K to basically trigger a secondary ignition. When you look at firebrands, we will have a presentation by Dr. Goldner tomorrow afternoon. That's much more complex and not as well understood. So one possible criterion is to say that the amount of embers, or in terms of mass of ember, accumulated mass or mass flux of embers that is accumulating at a given location has to be above a critical threshold values. I think a lot of the fundamental studies on firebrands are trying to tell us what is the criterion that we should use. We heard from Dr. Filkov about his way of looking at the problem with maps, that you can translate that. He was counting the number of embers. You can transfer that into maybe accumulated mass as well. So we are still waiting for the best way to formulate conditions for spotting ignition. One thing, even though I say I don't do chemistry, I have to pay a lot of attention to chemistry. If you look at the amount of money that is spent on wildfire research in the US, it is not spent on people like me doing fire dynamics, fire behavior. It is spent on people who are looking actually at the evolution of the fire smoke, the plume, where it's going to land, and the composition of the smoke. And if you want to characterize the chemical composition of the smoke, you have to do some chemistry. In particular, you want to look at the negative impact of the fire smoke on human health, on the environmental system in terms of air quality, and on the climate system in terms of production of greenhouse gases. So typically, if you are an atmospheric scientist and an atmospheric chemist, you would pay attention to carbon monoxide, hydrogen cyanide as toxic species or fine soot particles in terms of adverse effects on human health. You would pay attention to carbon monoxide, nitrogen oxides, and particulate matter as well in terms of air quality. And you would pay attention on CO2, methane, and nitrous oxide in terms of greenhouse gases. Okay, these are the important chemical species that you need to pay attention to depending on which system you're looking at, the human system, the environmental system, or the climate change system. So in my community, we don't do enough chemistry, and I'm happy not to do too much, but I have to recognize that a lot of the important problems around wildland fires are actually related to the chemistry of the fire plume. All right, so this is my conclusion. Sorry, I've been a little bit longer than what I wanted to. But in my description of combustion, I'm looking, the community is looking as a solid fuel, to represent the vegetation biomass. We're looking at flaming combustion most of the time rather than smoldering, although we have to start looking at both modes. And you will hear about this tomorrow from Guillaume Morin. We consider that the dominant mode of combustion is non-premix flame. That hasn't been disproved yet, but there are premix flame combustion aspects that are important for ignition, and Sarah McAllister will talk about that tomorrow. Our flames are buoyancy-driven, which make them a little bit unusual. Most of the combustion science literature is focused on momentum-driven flames for engine application. So sometimes we have to really explore the new physics associated with buoyancy-driven flames. Our flames are turbulent for sure. we have to look at wind and flat terrain and slope terrain effects. And the flame I was looking at was basically non-spreading, but you have to put this in the context of flame spread. And again, Sarah McAllister will talk about this tomorrow. I think I'm going to, I don't need to go through this. I wanted to say, okay, like any good podcast, you say, okay, what should I read? Okay. So if you want to learn more about fire dynamics inside compartments, I recommend these resources. So you have a book, 2 books written by Jim Quintiri. The first one with his colleague, John Carlson. Jim Quintiri is an emeritus professor from this department, so of course we're a little bit biased when we advertise his books, but these books are very good and contain a very good description of the physics. And we have Dougal Drysdale from University of Edinburgh. These are basically the pillars of our field right now for compartment fires. And last but not least, I think if you want to learn something about wildland fire behavior beyond what I hope you're going to learn this week, you should look at the book from the Missoula Fire Science Laboratory. We have 3 co-authors in the room, okay? So we have Mark Finney, Sarah McAllister, and Jason Forhofer who are here. So you can even, I think, buy the book and get it signed. Maybe for a discount, I don't know. But this book is an excellent introduction and description of the problem, and it's also it doesn't have a lot of competition, unfortunately, because this is a much-needed book, and we need more of that material. Let me stop here. Thank you. Yes, please.
Thank you very much for the lecture. With regards to the modeling of fires, how can you account for radiative losses if you disregard the infinitely the finite rate chemistry affects the formation of soot particles?
So your question is about radiation, right?
Yes.
So and it's a question about modeling or in models. So in any fire models, whether you use FDS, fire foam, open foam, or any tools that I'm aware of, you're going to have a radiation model that typically is pretty sophisticated. I think that's always been a strength of the fire science community to actually pay attention to radiation that is so important for us and come up with good model description and good analysis for radiation. So you have a solver for what we call the radiative transfer equation that describes the transport of radiation due to electromagnetic waves in space. So radiation is a bit unusual because it's a way to transport heat, but at the speed of light. So it is not your typical CFD phenomenon where we have convection that transport information. So there is no convection because everything goes at the speed of light and it's hard to go faster. So basically you have no delay in the transport of energy in radiation. So there is a specific equation that is called the radiative transfer equation. That is the basis to calculate radiation transport in fire models.
My question was more about you have radiation from gases, but you also have radiation from soot particles.
Right.
And if you neglect the formation of particles in the model, because you assume infinitely fast chemistry and all those things, then you are missing a part of the radiative losses.
Right. So okay. So if I stay away. If I look at the radiation from a flame, let's look at a flame. So you are saying correctly that the flame is going to produce soot, and soot is going to be a dominant factor in the radiant emissions to the surrounding. So you can describe that piece of the physics in 2 ways. You can try to come up with a good soot model, but now I'm kind of old enough to see how much of a dark hole soot research is for people who have to deal with it. When I was a young student, everybody was trying to study soot. Now I'm not a young student anymore. Still, there are a lot of people trying to study soot, and the progress has been fairly limited in terms of having, not in terms of the fundamental insights, but in terms of translating this insight into engineering models. So we still don't have the full understanding of soot physics and chemistry, and therefore we don't have good engineering models. So basically, you could try, and we have people in the committee who are trying to develop soot model, but it's hard. And I think we are going to hear tomorrow from Dr. Peter Sunderland about modeling of soot or description of soot physics. So the shortcut to avoid this problem in the community on fire modeling that I belong to has been to use a global radiant fraction. So the global radiant fraction makes an easy assumption that the radiant emissions from CO2, H2 or soot, doesn't matter, is going to be proportional to the heat release rate of the flame. So, and the coefficient of proportionality is called the global radiant fraction, and you have to select that coefficient of proportionality carefully, but it can be calibrated against experiments. And so once you are doing this, you don't need to describe the details of the composition of your combustion products, and you can have, you don't need a soot model anymore. So this is, that has been a fix, and that fix is still very current. I don't know how to do better for many of the simulations we do. So we use that fix, that bypass, if you want, often in our simulations. Yeah. Yes, please. Yeah. No, I was checking the time.
Question regarding the Q star parameter that you just said. So is it the same parameter that decides the brick size of the flame structure to be simulated?
No.
No?
No, I think there's a lot of misleading discussion in the literature about how to design a computational grid. For me, to design a computational grid it's a signal processing problem. So you have a flame with a characteristic length scale, a height, a width. It's going to change. Maybe it's a boundary layer flame. It's a thickness of the boundary layer, things like this. So you have a flame that has a certain geometry with characteristic length scale, 1, 2, or depending on the problem. And what you need is a grid that can basically capture the variations of that characteristic length scale. So it's a signal processing argument. You know, you can do it in space or in time. You need to have to resolve a variation. You need to have a number of data points across that change in the gradient. Okay. And that is a viewpoint that adapts to the pool fire situation where you can translate that into a Q star parameter because the flame height is a function of Q star. So, but to me, it's better to forget about Q star and to talk about flame height. Okay. If I look at, we don't have, I don't know where I was looking for the sprinkler protection in this room, but we don't have one. So, over there. Oh, okay. So they are there. So if you look at sprinkler protection, so you have these sprinkler detectors, sensors that are at the ceiling. When you simulate this with a fire model, whether it's FDS or OpenFOAM, you have to calculate a boundary layer. Okay, it's not a flame problem. You have the flame that is maybe above this table, and then you have a plume, and you're going to have a ceiling jet. So you have a boundary layer of hot gases that is going to hit this detector. So if your goal is to calculate correctly the activation time of that detector, you want to capture the heat transfer between these hot gases and the detector, and it's a problem of resolving the thickness of the boundary layer. So to me, the length scale viewpoint is a viewpoint that adapts to every piece of the physics in fire behavior, and it's a much better viewpoint than talking about Q star. Yeah. So maybe, Domingos, you're going to have the last question.
Thank you very much for your very illuminating lecture. I'd like to ask you, sometimes I have the problem of considering the flame as a solid body, let's say, because it divides two sides of the flow, as you showed in which conditions can we not consider a flame as a solid body? I am referring to that diagram showed that the graph is no longer holding that law of the fluid number on the left edge. Is that the field?
Well, so I'm not sure because your last comment takes me in another direction. I thought so. The flame description as a solid body, I think you have to be very careful, and I think some of the work again at Missoula has shown the importance of these buoyant instabilities. That means that even a line fire is not something that is two-dimensional, it is three-dimensional. And you're going to have peak and troughs. so that you can have air that can go to the other side of the flame without being deflected if you account for three-dimensional structure. If you treat this problem in 2D, then the flame looks like a kind of a solid body and all of the air is deflected above. And so what this means is that a 2D simulation is incorrect. A 3D simulation, we capture the physics that describe more of the flame structure. So does this answer your question?
Yes. But if you take a section of any 3D flame, when can you consider that it is impermeable to flow? Let's say there is one flow on one side and there is another on the other side.
Yeah, but what I've learned from the simulations we've done and after the insights that were developed from experimental observations at Missoula is that it's better to view these problems as 3D, really. So even I don't want to look at them as even the way the air is going to be deflected around the flame, I think I see it as a three-dimensional picture. It doesn't go up, for example. Again, in a 2D picture, you would say air coming in and strong buoyant motions, and you're going to have all the air deflected to the top. But it doesn't seem to be occurring this way. The air will go on the sides. And so I think I'm trying to train myself to, and looking at our simulations too that we have done here, look at a three-dimensional version of that picture. So I'm the speaker and the session chair, so I have to stop myself. So thank you very much.